learners, welcome to CS203, and I'm Hong Wei. I'm an associate professor at UC Riverside, and so I have a lot of experience in many different places, including industry experience in Google's TensorFlow Lite. So I do have a lot of insights that I can share with you throughout the class, and I have a lot of hobbies, but because we are short on time today, so we don't want to dig in those details, and we can know each other more always after later in the class. However, right now, there is one thing that I do want you guys to try. This is actually the main tool that we are going to use a lot in the class called Pull Everywhere. And then after you log in this, there are several questions that I'm going to ask you. So first of all, don't be panicked if you didn't get logged in, but right now I'm logged out. Okay, so you will see I also have to log in. So to log in, I have to use that. Okay, all right. Okay, so first of all, I want to ask you a question. What's your, oh no, it's, let me see. You know, sometimes when one thing goes wrong, everything will go wrong. Let's do this. T4. All right, so right now, my question is, what's your most CS topics, most favorite CS topics? And here is the same QR code, and you can respond after logging with UCR as what I just showed you. And then write down your response. Thank you. You saved me. Oh, thank you. Okay, so check. Let's see. Okay, the music was not out. Okay, nothing really works perfectly here. Okay, so based on your response, I think first of all, I want to say you guys are very honest because I don't really see anyone talk about architectures. All right, so now let's talk about why are you taking CS203? Okay, requirement, core. Okay, like as what we can see, core requirement. Some of you say interesting. Okay, very interesting. Like worse. What does that mean? Uh, important. Okay. I like to see that word. Hardware software interface. Is that okay? All right, but like your answer shows that the only reason why you guys want to take this is probably core requirement, right? So, and in fact, that's what I would expect, because typically, like I'm a computer science major, so I know what other of my cohort would think. So whenever we talk about what do you really care as a computer scientist, you are always thinking about like algorithms, data structure, software engineering, programming language. But in terms of computer architecture, this is your feeling, right? Like you don't care, right? So I thought there should be a music somewhere. Okay. Is the volume muted? Give me a second. Okay, I will check that later. But now let's talk about like, so if you check, well, these days people like to ask generative AI questions, right? So if you ask generative AI questions, when you talk about like what's the most popular topic in computer science, you will see like nobody was actually talking about like architecture. But if you talk about what's the most important topics in computer science, then computer architecture immediately pop up. First of all, I try to use a brand new refresh account for this. So this is not an answer based on my preference, because these days, like people have been knowing that ChatGPT has the tendency of like pleasing who is asking a question, right? So that's why I want to do this. But like the honest feedback from ChatGPT or Google Gemini, they always say that computer architecture is one of the very important topics. So I would say, and this is not just the response from generative AI. If you ask about like the father of like deep neural network, Jeffrey Hinton here, he would also say the same thing. Like computer architecture is very important. For some reason, the audio is not playing. Let's see. Is there a reason why? Um, yeah. Okay. There is. Did you guys hear anything? No. Okay. Okay. I really want you guys to hear that. Let's see, what can I do? All right. Let me use my speaker and see if that's loud enough. I think a lot of the credit for deep learning really goes to the people who collected the big databases like FaithAD, and the people who made the computers go fast, like David Patterson and others. Okay, so for those of you who can hear what he said, how come I'm not able to get on? Right, so he's basically saying that a lot of credits of deep neural networks goes into like people make the database faster, like Fei Li, and people who make computer faster, like David Patterson and many others, right? So, but who is David Patterson? How many of you heard this name before? Who is David Patterson? Who is David Patterson? How many of you checked the website? Can you do a quick search on David Patterson? Like David, you'll probably find it. So David Patterson and John Hennessy, they are actually the author of our textbook, right? So what does that mean is that computer architects, we are actually the ones who enables deep learning. And so many cases, people don't really consider computer architects as credits in any computer industry. So I always consider us like the hidden figures in NASA or many, many different places. Like we have contributed a lot, but nobody really give us the credits. But I'm okay with that because I'm a low-key person. I'm a very introvert, so I'm okay with that. But now, one thing as an educator, as a teacher in computer architecture, I really want you to recognize what is computer architecture and why is it important to us. So what is computer architecture? If you use generative AI models, they will tell you is the concept of conceptual design and fundamental operational structure of a computer system. And it's a little bit too wordy from their answer. So let's take the dictionary explanation, which is just one sentence. The manner in which components of a computer or computer systems are organized and integrated. That's computer architecture. So basically, you can consider a lot of people would think about computer architecture is something down to circuit level, but I would say that's a definitely no thing. Computer architecture is talking about how, with these components being built already, how are we going to use them efficiently, both in a way of assembling them as a system, both in a way of using them as resources when we run our applications. So it's not really just about the hardware. So a lot of people have the arrogance saying that, well, this is a class that I've been taking for a long time ago, and I am not really interested to it. So right now, I really want you guys to recognize where we are now as a computer science major in computer architectures. So now I'm inviting everybody to stand up a little bit, and we are going to have some little exercise. So for each of the questions, we will have two sides. If you agree with the statement on the left-hand side, on the right-hand side, if you don't agree. So now look at the question, choose one side. Left-hand side, right-hand side. Yeah, stand up. But I have to figure out. Okay, processors and memories are essential for all computers. Okay, so everybody stay here. Second question, Moore's law is still alive. Okay, make wise decisions, make wise choice. If someone survived until the end, I will give you $20 for Amazon credits. Okay, so where is the separation? Left, right? So that side? Okay, you can have a sit. Have a sit. Really? Yes. Now, here are the survivors. If you are standing, you are welcome to come here. We will talk about that later. Okay, like here. Okay, so these are the survivors. Now, second question. A third question, on the same machine, problems solving the same problem using fewer operations will have shorter execution time. So this is the line, right? What do you think? Okay, you want to be different? Okay, this is the third question. Okay, can't believe that. No. Oh, yeah. Okay, so okay, yeah. All right, so still survivors. Now the next question: an algorithm with lower computational complexity will have shorter execution time. Okay. Generally, if you think that's not always true, you can stay. Other people can sit. But you have to pass other 5 questions. Okay, next question. So it's like your show, right? Ninja Warrior. On the same machine, algorithm implementations will have similar execution times. Are you staying? Are you staying? Okay. Keep staying. Next question. Bitwise operations are more efficient. You'll stay. Okay. Algorithm complexity is less important if we have parallel hardware. You're not moving? You'll stay? Okay, thanks for saving me 20 bucks. All right, so there are other questions like the smaller size of a transistor, the smaller the power consumption, and the answer is no. GPUs are not limited by Moore's law. That's also not true. Performance of GPU does not really match the demand of AI ML applications. So all these questions, it drives up a bigger question. Like, since being a computer scientist, you have been educated, algorithm is everything, computational complexity matters. So you thought this is enough, right? But now I'm going to tell you, this is not good enough. So that means, and some of you probably don't trust that, but let's start with some demos. So for this code, I have this if statement, right? So what does that mean if I have option equal to 1, that means I'm going to trigger this. So what's the best sorting algorithm that do you have in mind? Okay, so what's the complexity of that best sorting algorithm? And log n. Okay, what's the computational complexity of this pieces of a code? O of n. So if option is 1, what's the computational complexity? So this is n log n, right? This is O to n. If option is 1, I'm going to do this. What's the computational complexity of this whole problem? N log n, right? So if option is 1, computational complexity is higher, right? So now let's run a demo. Okay, it needs me to log in everywhere. Okay, so so for this particular program, what I'm going to show you is exactly the same program here, except that inside this for loop, to make the code simpler, so I just make that sum calculation into just one line of code. So now let's run it. First of all, I'm going to run it with sorting enabled. As you can see, sorting with the whole thing with sorting this like 256K elements, it would take 0.16 seconds. Now, let me not sorting it. How much time it take? 0.5. So it seems like if we sort, we increase the computational complexity. It also gives you more operations to work on. However, it's faster, right? After sorting your data, with sorting, it makes everything faster, right? So that's why on the same machine with fewer operations doesn't mean it will give you shorter time. Like doing sorting here is actually adding more operations, but it makes the whole thing faster. And adding a sort, we are increasing the computational complexity, but it's actually going to be faster, right? So computational complexity does not tell you the whole story, right? Do you feel like you want to get your tuition back from your algorithm teachers? Now, even with the same computational complexity, like these two pieces of a code, what's the computational complexity on the left-hand side and the right-hand side? Read it loud. I can't hear it. N squared, right? So they are both the same. And in terms of number of operations, are they the same? No, why not? What? But does that change the number of total operations? Right? And in fact, the instruction count is also the same, right? But let's check how much difference is the runtime. So for this, okay, I can run it again now. So the left-hand side is the version A, the right-hand side is the version B. And let's run. So for the version A, it takes 5 seconds to finish. And for version B, it takes 9 seconds to finish, right? The same complexity, the same amount of operations, you have different execution time, right? So that's why we can conclude that the answer of this question is also a no. Are you ready to yell at your algorithm teachers, right? So how about bitwise operations? So in many companies, they would like to ask you if you can do code like this. How many of you know that, like, know this kind of question before? Yes, right? So, but is it really a good practice? So now, let me run this demo real quick, right? So on this fresh run that I just made, 0.04 versus 0.044, right? The left-hand side is what those senior engineers would think this is the dummy, stupid code. The right-hand side is the code they think is smart. But look, regarding performance, it's actually worse, right? And this pieces of code is not easy to understand at all, right? So leveraging bitwise operation in C doesn't really make your program faster, right? Now, talking about algorithms. So quicksort algorithm, as many of us know, is n log n. I'm going to tell you another algorithm called Platonic sort. Because of the time sake, trust me for now, this pieces of code, it has a sorting a complexity called n log square n. So the computational complexity on the right-hand side is higher than the left-hand side. Do you agree with that? Now, let's take a look of what's the real runtime. So this is the quicksort CUDA version, and this is the Platonic sort CUDA version. And Platonic sort, it has the swapping part as well as the driver part. And the driver part is essentially a log n times invocation of this n log of this internal n square log n thing, right? So if you run it, then this Platonic sort, if I just want to sort 256K numbers, it takes 0.1 seconds. But what if I want to do it with quicksort? Then let's take a look. And this is already ignoring the data transportation as well as the a lot of other things. So as you can see, 8.5 seconds. Right? So some of you might be thinking about, well, you're just testing small data sets. What if we have larger data sets? So if I have larger data sets, right, which I ran previously, it shows this is, if I sort like 1 million numbers, right, it's 0.1 seconds still. However, if on quicksort, is 134 seconds, right? So what does that mean? First of all, algorithm complexity is less important if we have rich parallelisms, right? So why we want to learn computer architecture? Because most of the time we use our imagination as what people told you about what a computer is. And you use your imagination about the computer you are using, right? So most of the time, you might think about this is the beast I'm dealing with. And you might be thinking about, I have a very powerful computer. It can do this and do that. However, you might have a different beast than you could ever imagine. And if you don't use it wisely, you are not going to achieve the effect that you want, right? So that's why we want to study computer architecture. So the big picture of computer architecture is the von Neumann architecture in a way that every computer is right now a von Neumann computer composed of the following components: a processor and the memory. So I don't know how many of you ever look into the detail of the computer hardware, but I do have a few components that our TA helped us to bring in today. First of all, oops. All right. So this is typically what you would see as a computer when it's in operation, right? You will see this motherboard. And first of all, you would have a heatsink here. And if you take it out, you can pass it along if you never see a heatsink, right? There is a socket. And on this socket, you will see a processor, right? So if you never see a processor, just pass it along and be careful. I can still resell it. And also, a lot of you use GPU a lot, but you probably never seen what a real GPU looks like. So I will show you a few GPUs. First of all, this is a very heavy one. Be careful. This is an NVIDIA T40. It's not in use right now, but I believe it's still useful, so be careful. So this giant box, you can imagine if we take it out, it will be something like this in a way that there is a baseboard, and on baseboard there is also a chip, and there is a heatsink to dissipate the heat. And so this is So you can see, right? This is the motherboard. It has processor and DRAM slots. Oh yeah, forget about the DRAM slots, right? So this is the DRAM slots, and this is the DRAM module, right? So if you take a server machine, a lot of people thinking about, okay, server, they are more powerful, but even for servers, they are still composed of processor and memory. And for a laptop computer, again, processor, memory, as well as GPU, right? And also for like a mobile phone, still, this is the mobile phone of mine. I didn't tear down mine. This is something from the network. And then you can also see processor and memory, PS5 processor and memory, right? And even though you have a Switch 2, I got a new one, but I haven't tear it down, so I don't want to show you the picture. I believe you can still see processors and memory. Well, Tesla, forget about Elon Musk, but if you look at the Tesla, the main component of the Tesla is essentially two processors because they want redundancy, as well as a set of DRAM. So Tesla is essentially also a computer, right? So processor and memories, they are everywhere. And the reason why we want them to be everywhere is because every computer is essentially a von Neumann computer. So what does that really mean by von Neumann computer? So it means that we are running machines in this way. So John von Neumann designed this von Neumann architecture in a way that we define in computer systems, we should have processor, memory in the very beginning. And then he didn't talk about secondary storage. However, I still include the second storage in the picture because we cannot imagine that you generate something without saving it, right? So, but what typically would happen is that saying that I have this line of code, I would use some language framework to generate machine code and binary formatted data as an executable. So within an executable file, you will find two sections, the text section, which contains the instructions, and the data section, which contains the global data you have. And then when we want to run a computer, we load a program into the memory, and then the processor would fetch instructions from the memory and looking into this instruction to decide what to do and drive up the corresponding components whenever necessary. But why von Neumann architecture is so popular? Because it basically tells us by loading different programs into the memory, your computer can perform different functions, right? So that's why processor and memories are everywhere. And I guess we can skip this. Now, so in the past, people always contribute to the performance gain to Moore's law. So if you could have remind yourself what is Moore's law, it basically says the number of transistors we can build within a fixed area of silicon doubles every 12 to 24 months. And if you have never read the Moore's law paper, I'm going to give you a very short recap how to read this paper within 30 seconds. So first of all, Moore's law is saying that integrated circuits, they are increasingly popular and they are very well established so you can trust them. And they are more and more reliable, so please trust them. And they could be made really small. But how small it could be, here is the projection that they are getting smaller and smaller. And as you can see, it's a straight line. So that's why people have that Moore's law based on this figure's projection. And then heat is a softball issue, so don't worry about it. And designing integrated circuits could be really easy. So please become a computer engineer. That's what basically Moore's law paper is about. If you don't trust me, dig into the paper. These are all the details that you need to know. So people have different thoughts about Moore's law, right? So Intel, well, this guy is already retired. Force retired. I should update it. It says Moore's law is alive and well. This guy, he said Moore's law is dead, right? But what's the reality? So as a scientist, you should definitely grab the data by yourself and figure out, right? So a lot of cases, people just trust what other people said. And these days, people just trust what ChatGPT said, right? But is that true? Is that right? Right? So let's grab the data. So this is the data that I grabbed from all the silicon products since 1970 to 2025. And this is the density of transistors. And then if you draw a line, is it changing? Are we still following the line? What does that mean? Is Moore's law still alive? Right? So now you know who to trust. But unfortunately, successful people do not mean they are honest people. Right? Look at business, look at, I don't want to talk about that because I still need my job. Right? But you know, a lot of cases, there are lots of things that you think I can believe, but you know, like don't just receive those information without your own judgment. And based on our own judgment, right, you can clearly see, these are all from the public data. Moore's law is still alive, right? Moore's law is still alive. However, the problem is that the CPU performance doesn't go with Moore's law. So there are something else going on. And because of the problem with the sound, I don't think I can play this video, but it definitely says we have met some trouble in scaling the single core performance, right? So now, as you can see, and the main problem is because the power density. So we start to have trouble of bringing down the heat per transistor. So a lot of people would think GPU is better for that. But actually, I would say NVIDIA is the biggest liar about this. Because if you check the power consumption per transistors, with newer technology, like this, between these two generations of TSMC nodes, you can see per transistor power consumption actually goes up from 7, like per billion transistor power consumption actually goes up. Right? And the power consumption per card actually goes up a lot from 400 to 700, right? So NVIDIA, that kind of company, they don't care about the heat dissipation for their customers, so they think it's okay to make it up for 700. But for a company like Intel, they are more responsible for the heat, partly because we want to put the processor in very thin devices like your laptop, right? So they cannot really make the device really hot. So that's why the heat is a big issue. But if you can ignore the heat, you can definitely unlimit the power, unlimit the performance gain with Moore's law, right? So Moore's law is still alive, but the power consumption is actually the main problem limiting our performance for now, right? So GPU are not limited by Moore's law, yes or no? If you take into account the heat dissipation issue, still limited by that, right? So it sounds like there's no way we can get hardware in the future, right? Especially if you pay attention to the demand of AI ML. It's far beyond what the hardware can do now, right? So as a software engineer, you have to be really innovative regarding how we use this hardware instead of just writing Python code and waste your hardware resource, right? So why do you want to take this class? Because algorithm complexity doesn't work well with real computers. A lot of people, they just write their code based on their intuition, learning from the algorithm class, but that's actually a wrong. Processor memories, they are essential. However, they are not faster anyway. So as a software programmer, you really need to think how to make the computer, how to make your program more adaptive to this new dynamics of our computers. So this class, we have a vision. We want everyone to be able to become a programmer who write efficient programs that saves time, power, energy, and carbon footprint. And we want you to be able to use the knowledge of computer architecture and the general guidelines to identify performance problems and design solutions to tackle the challenges of real-world problems. And regarding the learning experience, most lectures okay, a few slides. So I know there aren't that many good news that you can hear today regarding the job market of computer science, right? So really, there are still people getting jobs in computer science. So I also hope, so a lot of people don't want to take CS203 because they think this is not a class that would help them getting a job. But if you think the class in this way, what kind of skill set that I can develop through this class? Here are the few things that I am envisioning each of us can get. First of all, practice performance programming on large-scale projects. The ability to analyze and diagnose performance issues on real problems, real systems. Work thoroughly on each project, each concept, and think thoroughly on each concept, and answer question properly, precisely, with insightful data, right? So how are we going to help you with that? That's about our learning experience. So as you already imagine, I'm kind of like a game show people, so I don't like the lecture, like just pushing information to you. Instead, I want you to engage and participate, right? Like Ninja Warrior or whatever, right? So our method is basically read, think, discuss, learn, and practice. By reading, because you want to participate in, sometimes the speaker is working, sometimes it's not, I don't know why. You want to participate in, if you want to participate in Ninja Warrior, for example, right, you need to do some gym exercise before you go there, right? So the gym exercise that we have for this class is basically require you to read this assigned papers and textbook sections so that you have some basic ideas where we are. And during the class, I will bring questions like those 10 myths that I show you to encourage you to think. So some of you might get very frustrated about a question in the very beginning. And I want to say sorry about that, but I also have an excuse for that, because those questions, they are made intentionally to get you wrong. Surprisingly, people don't remember good memory, good experiences, right? You always experience the access, you always remember the access that make you feel the sad most, right? You always know, you always remember the name of the worst teacher that you ever had, right? Maybe the most hard to deal with person in your life, you also remember, right? So sometimes I intentionally make these questions hard and make it wrong because I know that people would try to memorize and try to enhance your knowledge about those questions you get wrong, right? So this is why we wanted to think thoroughly about this question, practice those questions, get it wrong, discuss with others so that you can learn and practice. So before the lecture, we have the reading quizzes, 20% of your grades, and it's on Prairie Learn. And at the time of the lecture, as you already seen, just join the poll everywhere, and you will earn credits from answer at least 50% of the questions, and then you will get 4 credits for 1 assignment. And we also have interactive assignments, which is based on Jupyter Notebook. So please watch this video before you start each Jupyter Notebook assignments, and there are already 2 up. So you can definitely check. And this time I'm doing things differently. So we are going to use computer-based test from Prairie Learn, and you are going to take the exam at the computer-based testing center offered by this campus. So there will be multiple available slots that you can choose. There will be dedicated people there to proctor you, so I don't have to be there. You won't see me if you hate me. On the other hand, a lot of people are always saying that, well, can I reschedule the final time or midterm time because I have this and this, which sounds ridiculous. But but now with this, right, you can schedule at like typically like a range of a week, within a week window. You should be able to find a time that fits you, right? So that's the benefit of computer-based quizzes and exams. So, but what I require you is to schedule your exam at this place. And those links are on our website. Logistics, we are going to have 20% grades on your reading quizzes, 30% on assignments, 20% on midterm, and finals for 30%. And participation, so I know some of you don't like to show up in the class, so I make it somewhat optional in a way that it counts as an assignment. So if you really don't want to show up, just make sure that you ace all the assignments. And we have two types of assignment, programming assignment, and this time the programming assignment is about optimizing a large language model using the computer architecture knowledge. So the first one, which is due in next week, you are going to at least use the profiling tool to know what's the most critical function to optimize. And then we are going to use the knowledge of cache optimization and finally parallel programming, right? So this is me, and we do have a TA right here. Jack, do you want to say something? Yeah, fun fact, or office hour, anything you want them to help.
Hi, my name is Jack. I'm a second year PhD student. And guess fun fact, I used to be a film major. So you can say I went from shooting films to shooting errors. Yeah, I guess that's it.
Okay, all right, so subscribe to our calendar. Wait a moment, I have the right time here. Anyway, so here's the website. Check our website for most up-to-date information, and sorry for messing up the time. It won't happen. I promise that, right? So, but here's a summary of our course resources, and everything, every link you can find through our website, right? So I don't think I have to go through this group, right? I don't have to go through this thing with this group, right? I can trust you guys, right? Okay, I trust you guys. Other than that, hopefully we can have a very enjoyable quarter. Sorry for being late on this. The next lecture, it will be on time. It will be 11, and it will be good. All right, I will still see you next Tuesday, right? Okay, I will see you next Tuesday. All right. Enjoy the rest of your day. Again, check the website. And also, we have reading quizzes due next Tuesday. Make sure that your Gradescope account is associated with your UCR ID. Assignments are released. Check those links online. And for those hardware components, please return.